Time again for a little more Physics 142. In this video, I'm doing more examples of Ampere's law, and I want to just think for a second a little bit more conceptually about Ampere's law and use it to understand something about permanent magnets. So I've drawn here a permanent magnet, maybe the north end and the south end of a permanent magnet here in black. All right, so that's just, some magnet I pick up off the street, you could order, and maybe find in a hard drive, something like that. And I've drawn a few field lines in this magnet. Remember that magnetic field lines goes through magnets, right? And that magnetic field lines always loop back and connect to themselves, right? So this is something that we've learned about magnetic field lines. But something that I want to think a little bit about is that, well, Ampere's law told us that if we take the integral over some loop, right? If we walk in this B field and we take some loop, if we integrate over that loop, that's going to be mu naught times the current enclosed in that loop, and by enclosed we mean going through the loop, right? And so there's something I want to think about here for a second. I want to think about, all right, let's think about just one of these magnetic field loops here. All right, so here I've got a nice loop. I've labeled it number 1. I'm just thinking about this loop right here. All right, so let's think about that loop. And from Ampere's law, I guess the question is, what can we conclude about what's going on in that magnet? Right? What can we conclude? And I'd like you to think about that a little bit. One thing that you might be able to conclude here, one thing to think about is that, well, if there's magnetic field here, right? If there's magnetic field, and if I, go and I walked in a path along this loop, I would definitely get some positive value here, right? That means that there must be current enclosed in it, right? And specifically, there must be current. Well, there isn't going to be current in the empty space, right? So there must be current in the magnet, right? In the part of the magnet right here that's enclosed, right? That there must be current in there. And you could actually also figure out the direction of that current, right? We know that magnetic fields loop around current, right? And so we know that this current must be coming up out of the page, right? That you can, if that the magnetic field lines are going to sort of curl in this direction, and that means that the current must be coming up out of the page here, all right? So we know there must be current in the magnet, and it must be coming up towards us, coming up out of the page. And I think that's actually sort of an interesting thing, because we might ask, permanent magnets, we don't generally think of those having currents in them, right? How can we make sense of that? And one way to sort of make sense of this is to realize that individual atoms have sort of their own little magnetic fields, all right? So, one model of an atom, sort of the Bohr model of an atom is what it's called, right? Where we have a nucleus, all right, that has sort of a positive charge, all right? And we can think of electrons as sort of orbiting around that nucleus, right? The electrons are moving around that nucleus. Well, and when you have moving electrons, right? Moving electrons, that's moving charges, that's current, right? That would be some current here, right? And if we have current, all right, then that should create some sort of magnetic field, right? If we have, something going in a circle, right? Current going in a circle, we realize that current loops, the magnetic field then is coming out through them, right? We loop around, the magnetic field is coming out through that loop there, right? So, this might create some magnetic field down, sort of like that, all right? And the deal is that, well, this is true for all atoms, right? The ones in your body, whatever, but you're not a permanent magnet. So what happens in a permanent magnet is that all the little magnetic fields from all the atoms all get aligned, all right? So we should say in permanent magnets, all right? In permanent magnets, what happens? Well, all of the little all these little orbits, right, all the magnetic fields of all the atoms get aligned. All right, so you have some structure, all right, that some structure locks atoms into place so the magnetic fields align. All right, and so we can think about there actually being currents in here. Well, where are the currents? They're all little itty bitty currents, all right? They're on the atomic level. You have little currents on the atomic level, all right? But all those currents in a permanent magnet, they're all going the same way, so you're all producing magnetic fields that go in the same way. And that's what's happening in a permanent magnet. So ultimately, even though a permanent magnet just seems like, some rock that has magnetic properties, ultimately, it's the moving electrons in that metallic or whatever sort of material you have in that magnetic material that end up creating magnetic fields. And so we can sort of see that from Ampere's law, all right, that it has to be enclosed current connected to magnetic fields.